let's look at the hidden killer within every single LLM. Now, lots of people assume it's computation. However, that's simply not the case because our GPUs are extremely fast. The real hidden killer is the weighting and the more specifically the memory of the LLM. Now, this is because GPUs have a memory hierarchy where the initial what's called tensor cores are really fast, but they hold almost nothing in terms of memory. Whereas you get to registers and then SRAM and then HBM, and HBM, as you can see, is the lowest part of the hierarchy, which contains the most memory. However, it's super slow, right? It takes lots of time to go from the tensor core to the HBM. So that stalling is what kills LLM's performance. In this video, we'll be covering that at the very beginning. We'll be doing the code, and then we'll be covering the actual in-depth GPU low-level kind of realization of what flash attention does. So, if we grab any token, doesn't matter the amount, we have to multiply it against itself because an LM has to look at every token against every other token to determine, what's important. Now that's quadratic growth, which is no good for memory. If we look at GPUs, right, their hierarchy, it takes a long time to get to HBM, and so it kills performance. Okay, now for the coding portion of this video, we'll be going over a function called flash attention reference, and it's quite similar to the actual concept of flash attention, although not exact. The flash attention reference will take in 4 parameters: Q, K, V, and block size. Now, if you're not familiar with transformer architecture, that's fine. I'll go over the very basic concept of what these parameters are. First is Q. Now Q is the query matrix, and it asks, what information am I looking for? K is the key matrix, It advertises what information do I contain. The V matrix is the value matrix, and it basically asks what information should be retrieved. Now, these matrices are quintessential to understanding how flash attention works because the actual equation for flash attention, which will be on the screen, is the computation of Q and K on that numerator divided by root D and so forth. So the QK matrix is where flash attention really shines because you don't want to materialize a matrix that is n by n. And what I mean by n is, it's a bit of a tongue twister, is you have given, some matrix n by d, right? Or same thing as this q, right? You have an n by d matrix, and then you multiply this, right, by an n by d matrix. In case you don't know what this at means, it's literally just, uh, textbook matrix multiplication. And when you multiply these together, the result will just be an n by n matrix. Now, also known as an n squared matrix. Now, this matrix is very, very, very heavy because it's all tokens multiplied against each other. They have to understand, well, I guess the model rather, has to understand what is important to what. Because of that, you're essentially left with a huge matrix that when, as you saw in the beginning of this video, when two elements are multiplied against each other, their impact or their memory space doesn't double, it quadruples, right? So when we first had transformers, we had to deal with that, and it was horrible, and we didn't like it. But some genius by the name of Tree Dow comes in and turns this n squared problem into an O of n solution. So that concept is what we'll be going over today. And this reference is just a implementation, very basic one, of that solution. So we have our Q in the shape of n and d, and then we define our scale, as you saw from the attention equation. Sorry, one more thing before we get into this. I totally forgot to mention what N and D were, as well as what O stood for, which we'll get to in the next part. N is the number of tokens available, or I guess input. D is the dimension of the attention head. And then O, the matrix O, stands for the output matrix. And in case you're not familiar with the syntax, it's essentially saying create another matrix with the same shape as Q, but initialize that all the elements rather, in that matrix to be 0. Now, for our outer loop, we'll handle the logic regarding running variables and, well, I guess the initiation of those running variables and the actual Q blocks themselves. So, as you've noticed, and maybe as you've seen, Q blocks are little subsections of the Q matrix itself. Now, because of that, we don't have to materialize the entire n by n matrix if we process those little tiles. Hopefully that's intuitive enough. If not, I hope the visual gave you enough of a, I guess, understanding of that concept. So we'll define a Q start and a Q end. The Q start will be from O to N in chunks of block size. The Q end will be the Q start plus the block size over N. Now our Q block is just going to be from the start to the end. Hopefully that's familiar to you in terms of syntax. The B, or the actual block, is going to be the Q end to the Q start. Now you might be asking yourself if this is, or rather asking me, if this is really necessary because it seems redundant. And the answer is yes, but we'll get into that later. For M, this is going to be a running variable. Now, M, L, and ACC, which stands for accumulator, is, or I guess are, all of our variables, or running dynamic variables, which will change over the loop as it iterates. M is our initiation of B, or rather, M is our maximum score over any given block. L is going to be our Softmax denominator. So as you, I guess, will see, the to get started with our dynamic variables, we first start with B, right? And you may ask yourself why these two are kind of the same thing. Well, we use them for separate purposes, but we'll get into that later. To explicitly define them now, I guess, would be this Q block is just a chunk of, the Q that's loaded into the SRAM. And the B, which is the actual block size, is just the block size. I mean, I don't know how else to explain it other than we'll get to their importance later, in terms of making sure they're different, or I guess defined separately. But onto M. M is going to be the running maximum score, which is just a 1D vector of shape B. It tracks the highest dot product score found so far in each row. L is going to be our running softmax denominator, which is simply just the sum. If you saw the attention equation, it's a 1D vector that accumulates the sum of the exponentials processed so far. ACC, or the accumulator, essentially holds the weighted sum of the value matrix, the values vector numerators accumulated so far in the query block. It's a bit of a mouthful. Now onto the inner loop, we have k. So we define k with v because their computation is essentially the same. Um, in other words, you have some block of k that you take out from the k matrix itself. That's essentially what v is going to be as well. So you define them together because that right on the k and v matrices is just going to be equal in terms of length and chunk size. So you simply define them together. Um, Although I'm not sure how helpful that you find that explanation conceptually, hopefully it makes sense when we look at the rest of the logic, which is not much, to be fair. The S is just the raw attention scores, right? Or I guess I should say raw attention scores for the tile, because you have the Q block and then the K block, right? Which is a little bit different from the actual attention mechanism. But you obviously have to multiply them by scale to ensure that it's local per block or tile. And then you update M. So alpha here is the exponent of the m minus m new. And this is important because it keeps track of, the actual exponential of our local chunk or what we're comparing. One thing I would like to point out, if it wasn't, you know, explained by the structure alone or self-explanatory, is the fact that you stream the K and V blocks along with Q every, I guess, Q chunk, you could call it. So every time we take a chunk of Q, we stream all of the K and all of the V against that Q. This might seem counterintuitive because you do in the actual attention equation, QK over the dimension and whatnot times V, and V is outside of the, I guess, parentheses. However, in this case, you do multiply K and V together against Q. So you're kind of streaming that. Um, okay, onto alpha and P. These two are a little bit different because despite this one being M minus M new and S minus M new, this one is kind of the key to the actual online softmax component. It essentially evaluates how much larger the new maximum is compared to the old maximum, whereas S is the unnormalized softmax numerator. So in simple words, it's essentially saying that alpha is it contains the maximum of the actual equation, and P is the unnormalized numerator. So one's a maximum, one's a numerator. And then we recompute our L, and our L is just going to be alpha times L plus P um, of the sum of that vector. And then our accumulator is just going to be the updated accumulator, right? And then we reassert M and L as M new and L new. And then it completes the logic of our inner loop for that specific KV chunk. We do the process of the actual softmax within that, and then we move on to the next Q chunk, doing that same process, right? After this inner loop is done, we use, or I guess we write O with Q start and Q end as the accumulator divided by L. And then we return that output matrix. And then we have finalized all the chunks such that O contains the output for each of those respective chunks again. So I hope that kind of intuitively explains the Softmax online processing of flash intention itself. I will be answering comments in terms of how helpful this was or what I could do to, better explain or better elaborate on what these variables are. Um, I will also try to answer in the comments if you guys have any questions, and then please let me know what I should do next. I will be uploading a few more videos in terms of just trying to get stuff out there, but yes, please let me know. Thank you. Now, to look at the actual HBM to memory, there's lots of steps in between. First, you compute, then you write, then you read again, then you compute again, then you write again, then you read them, then you multiply them, then you write, and that entire thing is one call. Onto the online softmax and tiling, right? This is the M that you saw earlier, right? For the running maximum and then the running normalized sum. Um, that's essentially what happens. For the SRAM tiling, this is the actual computation, right? You'll see Q, K, V. This is the actual tiling, breaking it up and putting it onto the SRAM or making it fit into the SRAM, right? So the entire thing never exists. Now, I have this running in the background just for a couple times to like explain the actual GPU architecture. So you have something called threads, which act as kind of a parallel processing core, and those threads are each given jobs to do in parallel. Let's say you have 31 threads, or 32 threads rather, and 31 of those threads are doing a really fast job, but the 32nd thread is doing something tediously slow. Now, the original flash attention kind of had the same idea as what we covered, it just didn't use the GPU as well as it could have. Right, as we see in this animation, we have the threads in flash attention 1 kind of being unutilized or rather underutilized, waiting for sync operations or halting for sync operations, which is when, as I just explained, what they wait for all the threads to be done. Whereas the newer flash attention or flash attention 2, I believe there's 4 of them now, they utilize the GPU a lot more efficiently. And so you're utilizing a lot more of the time, which is really good. Uh, so because of warp divergence and sync halting, or warp divergence is literally just that job of having each thread do a different job, taking different times, right? You have a lots of room for optimization left on the table.